Dear students, in this lecture, I'm trying to explain another approximation technique. We already explained the variation principle, time independent perturbation theory. All are the approximation technique for time independent to solve the time independent Schrodinger equation. The WKB approximation also another approximation techniques to solve time independent perturbation theory. So this approximation is proposed by Wenzel, Kramers and Brilliant. These are the three scientists. So that indicates the WKB. And this using this approximation technique, we can get the solution for one-dimensional Schrodinger equation. And actually, this technique is demonstrating the connection between classical and quantum theory. So it's also called classical approximation. Because why it's classical approximation means it gives the classical result when h cut is equal to 0. H cut tends to 0. So h cut tends to 0. In that way, this method is applicable when the potential is slowly varying. It's a very important point here. The WKB approximation is applicable only for the slowly varying potential. Okay. What WKB methods? The WKB method means a method to obtain the solution for a one-dimensional Schrodinger equation. So we start with how this is working. So the one-dimensional Schrodinger equation of a particle moving in a region of a constant potential V0. Suppose a V0 is a constant potential. So what is the Schrodinger equation? T square psi by dx square plus k square psi is equal to 0. And where k square is 2 by h cut square E minus V, where E is the total energy and V is the potential. And the solution for such a system is psi is equal to e power plus or minus ikx. This e power ikx, this means an oscillatory solution for all E greater than 0. Suppose the incoming energy of a particle less than 0, such case this solution becomes exponential solution. Okay, so but in this WKB method, treating the potential is not constant one, it's a varying potential. So I take the V is equal to V of x. If V is equal to V of x, k square can return as 2 by h cut square E minus V of x. Now the solution for the Schrodinger equation using this potential with the condition E, the incoming particle or the system energy is greater than the potential energy case. That case, I took a energy, the wave function of psi is equal to exponential I by h cut s of x. A new parameter I introduced here, s of x. So this s of x is something like an action-like quantity, and I will explain what is meant by s of x later. So I using this psi exponential I by h cut s of x, I am going to substitute this in this time independent Schrodinger equation, one dimensional time independent Schrodinger equation. So first of all, I need to find d square by dx square, and I need to find d square by dx square here. So d square I psi by dx square is nothing but is a second derivative of this much. So for that I am finding here for second derivative, and d by dx of E by I h cut, my mistake here, d square by dx square E power I by h cut s of x. And while I took a first derivative first, then there is a product rule I need to apply, and once it's the product rule I can do, and I get a result like this. You can do this one, simply a simple differentiation. Once I get this one, I substitute instead of d square psi by dx square, I substitute this one and plus k square psi, I get a equation like this one. ds by dx square minus I h cut d square x by dx square minus k square h cut square is equal to 0. And here are my first techniques of the WKB here I am using. I took this action like variable s of x as a powers, expanding this s of x as the powers of h cut. First term s0 plus s1 into h cut plus s2 into h cut square by 2 factorial plus and so on. So expanding s of x in multiple of or in the powers of h cut. So I substitute this s of x in this equation. What is going to happen? This equation 3 I am going to substitute in equation 2 and also I am neglecting all term order higher than h cut. So I am taking only the term s0x plus s1h. I am taking approximation here, the terms up to h cut. If you need, you can take more than h cut, but here I am taking an approximation. Now I need to find ds by dx square, d square x by dx square. So that's I am doing here, ds by dx whole square. I can get an answer because this is d by dx of s0 plus s1 h whole square. So just ds0 by dx plus h cut ds1 by dx. This a plus b whole square form. So a square plus b square plus 2ab form. I get a value here. And later d square x by dx square, and to take a second derivative here. This is simply equal to second derivative. And you have to substitute this ds by dx square and d square x by dx square everything in this equation. And I will get a form in this form. This is I put some term will cancel. I called it as equation number 3. The term here a term is here minus k square h cut square. It's included with a term independent of h. Actually the term is not depend on the h cut in the expansion of coefficient, because you can do this one here if you want. K square h cut square you can find 2m by h cut square e minus v by h cut square. H cut square will cancel. So this 2m by e minus v actually is not depend on h cut. So this much is the term with h cut is 0 with a, and this is the term with h cut as a first coefficient in order of 1. Equation 3 is valid only when the coefficient of h cut must vanish separately, because the right hand side is 0. So the coefficient of h cut is separately need to vanish. So I equating this first term ds0 by dx all square minus k square h cut square equal to 0. From that equation I get ds0 by dx all square is equal to k square h cut square, and ds0 by dx is equal to or minus k h cut. I get an equation from here. And from second portion, do ds0 by dx ds1 by dx minus I d square 0 by ds square is equal to 0. Here I am just finding ds1 by dx. I took the ds0 by dx in the right hand side. That term will come ds1 by dx I by 2 ds0 by dx. ds0 by dx is k h cut. I substitute that one k h cut here, and the d by dx of ds0 by dx. ds0 by dx is nothing but k h cut, and k h cut is the dx means dk by dx. So I by 2 k h cut into h cut dk by dx cut will cancel. The remaining answer ds1 by dx is equal to I by 2k dk by dx. So from I get this ds1 by dx also. And equation number 4 I get ds0 by dx. Using the equation number 4 I get the answer for s0. s0 is nothing integration over k h cut dx. So k we know 2m by e minus v of x root, because k square is equal to 2m by h cut square e minus. So here into h cut is there. So that way integration 2m into e minus v of x into r. From equation number 5 I getting s1x integration I by this dx you can say I by 2k into dk by k. dk by k integration will become log k. So s1x is equal to I by 2 into log k. I just multiply with is1 into I and I minus half log k. So is1 is nothing but log k minus half, because in the logarithmic rule a raised to b is equal to b into log a. Using that one log k log root k. So e raised to is1, I take an exponential here, e raised to is1 is equal to root k. So I getting here e raised to is1 as a root k. And now I have s1 and s2 s0 form. Now we already written the WKB wave function up to h cut as a into e power I s by h cut, where s is equal to s0 plus h cut into s1 using that approximation. But okay, substitute this one, a e raised to I s0 by h cut into e raised to I s1. H cut will cancel in second term, and s0 by h cut, I got an answer exponential plus or minus I root k dx. E raised to I s1 is equal to root k. The root k, sorry, 1 by root k. So 1 by root k will come in. So this is the answer for WKB wave function. So there's a two wave function is there, plus or minus. So the linear combination of these two will give a general solution. Okay. So the next point is what are the properties of WKB wave function. So here k is a real quantity. So for k being a real quantity, the wave function for e greater than vx is an oscillatory function. If k being a real quantity, for e greater than v of condition, this is an oscillatory wave function. The probability density psi star psi I can find, or psi star I can find a by k square, and the probability density is inversely proportional to particle momentum as expected classically. Classically also the same result we are expecting. So we are considering the second condition, that is the energy is less than the potential case, E less than V of. This is very important in quantum mechanics, because in this case, even though the penetration is forbidden classically this region is not allowed, because a particle having an energy which is less than the potential is rebounded according to classically. But in this case, quantum mechanically particle penetration is allowed. This region is therefore non-classical. So in this case, instead of k, I define a gamma square and another constant, that is 2m by h cut square. Instead of e minus v of x, I took a v of x minus v. That's all, and define a gamma square. Schrodinger equation become, instead of k square, and there is a plus k square psi, instead of here minus gamma square psi is equal to 0. If I take the previous same procedure, I get an end up with a result the same way, d by root gamma exponential gamma dx. Instead of exponential I gamma dx, here to getting a plus gamma dx, there is no I term is not there in this thing. That's only the difference. So the two solutions are exponentially increasing and decreasing, not an oscillatory solution. The E greater than V of, we getting an oscillatory solution, but here just a I term is not there, so it's not oscillatory solution. It's just a plus gamma dx means exponentially increasing, and minus means exponentially decreasing. That's all. What about E is equal to V of x? In this case, energy is equal to potential means that point is classically a turning point. The situation is usually called the classical turning point, because the particle will stop at this point. So you can, the harmonic oscillator, the particle is oscillating in this, like at this point, the total energy is equal to potential energy. So that is the turning point, because the particle will stop at this point and the rebounded classically. So in this region, k and gamma tend to 0 and psi tend to 0, and psi flop, because in this gamma or both k tends to 0, so it's become psi become at infinity at this point. At this point, WKB approximation fails. So E is equal to Vx at the classical turning point. WKB approximation is not a good one. So this is the WKB, how the WKB wave function we can find in this one. So I took a validity criterion for WKB wave function is we can find. The criteria for the wave function, the neglecting the in between I choose approximation where I took the terms up to h cut. So the neglecting the term beyond s1 in the expansion of s is valid only if in this condition h cut s1 by s0 much less than 1. So h cut s1 much less than s0 less than 1 is the condition. So I just rearranging this equation, h cut into ds1 by dx by ds0 by dx less than 1. We already found ds1 by dx is equal to I by 2k dk by dx, and ds0 by dx is equal to root k. Seeing this idea, I substituting here ds1 by dx I by 2k dk by dx and plus or minus k h less than 1. So I by k square dk by dx less than 1, and we know lambda is equal to 2 pi by k, or k is equal to 2 pi by lambda. From this one, k is equal to 2 pi by lambda. I substitute instead of 1k, k square is here, I put 1k is there, and instead of 1k I substitute 2 pi by lambda. So it's lambda by 2 pi dk by dx, and I took a modulus, so I is not there and less than 1. So this is the condition now. So this condition indicates, which means the fractional change in k, dk by dx by 1 over k is the fractional change in k in the distance lambda by 2 pi must be smaller than unity. Only if this condition is valid, then only the WKB will in the WKB approximation we can use this wave function psi is equal to by root k exponential ik dx or gamma dx form. So this is some basic facts about WKB approximation, and next lecture I will explain what is the connection between the two wave function e less than vx and e greater than vx, that condition. Thank you. Please go through this one, a textbook, notes and textbook. You may get a good idea. If you are in doubt, we can discuss in the next slide. Thank you.